All right, today we're going on a fascinating journey. We're going to watch a substance get completely broken down and then rebuilt into something totally new. This is a story of creation happening right at the molecular level. It's pretty cool.
So just look at this. This is where we start, with these really vibrant blue crystals of copper-2 sulfate. And where we end up? With this fine, jet black powder of copper-2 oxide. I mean, what a change, right? So the big question is, how on earth do we get from that blue stuff to this black powder? Our mission is actually pretty straightforward. We want to successfully synthesize, and that's just a fancy word for create, a brand new compound, copper-2 oxide, or CuO for short. Now, that word synthesis, it might sound a little intimidating, but it's not. At its heart, it's just about creating something. We're taking some simple starting materials, following a recipe, and building something new and a bit more complex. Honestly, it's kind of like chemistry's version of building with Legos.
So what's our game plan? What's the roadmap for this little creation journey? It's a simple 4-step process. That's it. First, we're going to mix our ingredients. Then, we add some heat. After that, we filter out what we've made, and finally, we dry it. Mix, heat, filter, dry. Let's jump into that first step. Okay, this is where the first bit of real magic happens. We're about to watch two liquids mix together and create a solid almost out of nowhere. And here is the exact recipe for that magic. We're mixing copper sulfate with sodium hydroxide. You see the little AQ next to them? That just means they're aqueous or dissolved in water. But look what happens when they combine. We get copper hydroxide, and see that little S? That's the key. It tells us it's a solid. This whole process, where a solid just appears out of a liquid solution, has a name. It's called precipitation. So if you were in the lab, you'd take about 0.4 grams of those blue crystals, dissolve them in water, and then you'd carefully add the sodium hydroxide. You give it a stir, you wait a second, and boom, you see a solid start to form. Oh, and here's a little pro tip. If the liquid around that new solid is still blue, it means there's still some copper hiding in the solution. No problem. You just add a little bit more sodium hydroxide to get it all to come out. We've made our blue solid, but that's not our final destination. Not even close. To finish this transformation, we have to put it through one final, crucial test, a trial by fire. This next chemical equation shows us exactly what that heat is doing. Our blue solid, the copper-2 hydroxide, goes through what we call a decomposition reaction. Basically, the heat gives it enough energy to literally break the compound apart. And what's left? Our final black powder, copper-2 oxide, and a little bit of water vapor, which just floats away. And this right here, this is the moment of truth. This is the most important visual clue in the whole experiment. When you see that pale blue solid turn into this deep, rich black solid, you know you've nailed it. You have successfully created copper-2 oxide. Okay, awesome. We've made our target compound, but right now it's just sitting in a beaker, mixed in with a bunch of liquid. So the next job is all about isolating our prize. How do we do that? Well, we use filtration. We just pour the whole mixture through a special piece of filter paper. It's kind of like making coffee. The paper catches all the solid black powder, our good stuff, and lets all the liquid just pass right through. We'll give it a quick rinse to wash off anything else. Then we take that filter paper, put it on a little glass dish, and pop it in a drying oven for maybe 10 to 20 minutes to get rid of every last drop of water. Now for the big question. We followed the recipe, we saw the color change, but just how successful was our synthesis? It's time to crunch some numbers and actually grade our performance. To figure that out, we've got to look at the data. We need to know exactly how much of our starting material, the copper sulfate, we used in the beginning. Then we need to weigh our final dry product to see what mass of copper oxide we actually recovered. Those two numbers, they're the key to figuring out how efficient we were. This all leads to a super important number called percent yield. The best way to think about it is like a report card for your experiment. It's a simple ratio. You take the amount of product you actually made, and you divide it by the maximum amount you could have possibly made. That final percentage, that tells you exactly how well you pulled off the transformation. So we did it. We successfully turned copper from a blue crystal into a black powder. But here's the thing. The basic ideas of precipitation and separation are universal in chemistry. So that leaves us with a final thought. If you can do this for copper, what about other metals? Based on everything you just saw, how would you tackle a similar problem, like, say, capturing chromium ions from a solution? What would your first move be?